So friends, we are meeting again. The series of distance protection of transmission lines. This is the 5th lecture on distance protection. And if I count the number of tutorials, it comes to 17. Plus practical tutorials are different. So I think I must have given 30 videos by now. So we start with the distance protection of transmission lines. 5 up to 4. We have covered the fundamentals. We have covered the different characteristics, basic characteristics, not the complicated characteristic. We have just covered the basic characteristics. And we have seen as to how the distance relay operates in 3 different zones. Now we go further. You see, as I was telling you last time, I had started telling this, that you say that V by I is equal to Z. And when I say that a distance relay measures distance, but it doesn't measure distance, it measures impedance, because impedance is proportional to distance. Impedance is R plus Jx. R is equal to rho L by A. So R is proportional to L, and in the formula of XL, L is there, and in the formula of L, that length L comes. So in any way, Z, the impedance of line is proportional to the current, right? But our biggest difficulty is that in the transmission lines, in the power system, different kinds of faults occur. Triple line to ground, double line to ground, and line to ground. Now, for all these faults at a particular location, distance relay should measure the same impedance. And unfortunately, it does not. So, it does, but we have done something. We have to do something for that. So, if we see, for three-phase fault, I is equal to V by Z1. And Z1 is the positive sequence impedance. So, Z1 is equal to V by I. So, that is true. So, if you feed any voltage and any current, line voltage and line current, phase voltage and phase current, not only line voltage of Ry, you can feed line voltage Yb, Dr, right? You can feed anything and you will get Z1. That is true. But that is not true for LL fault. For LL fault, the problem occurs. For LL fault, the current is root 3V divided by Z1 and Z1 plus Z2. And Z1 and Z2 are equal for transmission line and transformer, both, for all static equipments. So root 3V by 2 Z1. So it comes to Z1, it comes to I is equal to root 3V by 2 Z1, and that means Z1, it comes to this, that the measured Z1 is root 3V by 2I. Right? The measured impedance by the relay is not Z, is not Z1, but it is root 3 by V, root 3 V into 2 Z1. If you take V upon Z1 is equal to V upon Z1 is equal to I, then it will be root 3 by 2 I. So, I mean, different Z1 is there. It will not be Z1, but it will be root 3V by 2 Z1. So, and that thereby, if you see Z1 is equal to root 3V by 2I, Root 3 V by 2I is equal to V by I is equal to Z1. So is equal to root 3 V by into root 3 by 2, that is 0.866. That is the impedance measured from relaying point to fault point for the double line fault is 0.86 or 86.6% of impedance measured by the three-phase fault for the same fault location. So how can you derive the characteristics? It is not possible. For double line fault also, the impedance measured should be same. It should not differ. And if you go to LG fault, V by I will give some other value because the formula for LG fault is uh, Z, rather I is equal to 3V upon Z1 plus Z2 plus Z3 plus 3 Z1 plus Z2 plus Z0 plus 3ZF plus 3Zn, if at all if you have connected Zn. And even if you have not connected Zn, it is ZF. And mind you, friends, for LG fault, ZF may be quite large because LG fault means it is a flashover across the line insulator, and then tower resistance. Tower resistance is not as good as the SCSR conductor resistance because tower iron is not a very good conductor of electricity. Its resistivity is high. And then the soil resistivity. Soil resistivity will also differ from place to place. If you go to hilly area, the soil resistivity will be high. It is measured and it is said that the earth resistance ZF can be as bad as, or whatever you say, as good as uh, 20 ohms to even 50 ohms. And that is multiplied by 3 in the formula, right? Even if you have not connected Zn, that means deliberate impedance in the neutral circuit, even if you have not connected. And Z1 plus Z2 plus Z3 plus 3ZF, in that Z1 is equal to Z2, therefore 2Z1. And Z0, that is zero sequence impedance, is for 220 kV long lines, it is about roughly 4 times Z1. So it becomes 6 times Z1 plus 3ZF. So that makes the earth fault current, earth fault current so low that so often it is lower than the rated current also. And it cannot measure the true Z1. So how to make the relay measure true impedance? For that, we will have to do some mathematical analysis, right? Some mathematical analysis we have to pass through. That is not possible in this YouTube video. For that, you will have to subscribe the module 4 of power system protection, which will be soon uploaded on edupme, and then you can learn full uh, distance relay with full analysis, full mathematics, and you will be able to solve many unsolved questions also, right? And you will be able to get your analysis also. So all these things are there. But right now we will not do that. We will simply list out the quantities. The proof of that is given in that analysis, which is there in the module 4. So quantities to be fed are this. RY fault. If there is an RY fault, it is known as RY unit. RY fault is cleared by RY unit. YB fault is cleared by YB unit. And BR fault is cleared by BR unit. So this is the first thing, first difficulty. That for 3 different line faults, line to line faults, 3 different units are there and 3 different quantities are to be fed. Units are different. RG, YG, BG. These 3 units are also different for ground faults, and the quantities to be fed are also different. So, in the non-switched distance scheme, there are 6 different units. I am telling non-switched because there is something like switched distance scheme also. which we'll see afterwards. But in non-switch scheme, which people used earlier days, people used non-switch schemes. In non-switch scheme, people used this 6 units. So to RY unit, you will feed VRY and IR minus IY. IB unit, you will feed VYB and IY minus IB. And to BR unit, you will feed VBR and IB minus IR. RG unit, you will have to feed. That means what I'm trying to tell is that for YB unit, if you feed VRY and IR minus IY, it will not result in Z1. You will have to feed VYB and IY minus IB only. For BR fault, if you feed VYB and IY minus IB, it will not result in Z1. You will have to feed VBR and IB minus IR only. Similarly, for RG fault, VR, RG fault, you have to feed voltage VR and current IR plus I0 into bracket Z0 minus Z1 upon Z1. This I0 into bracket Z0 minus Z1 upon Z1 is known as compensated current. So you have to feed phase current plus compensated zero sequence current. That would lead to Z1. So if you feed these quantities from relaying point to fault point, irrespective of type of fault, relay will measure Z1 only. Right? That is very important thing, and that has to be there. Right? This we have seen that phase comparator relay we are feeding impedance reactance, so we know these characteristics. So when you feed Ki plus V, that I that you feed is from those quantities. You will not feed I, but for RY fault IR minus IY. So K into bracket IR minus IY plus V means V RY. That one has to take care. So no doubt one has to take care when I say so. The relay manufacturers are giving everything readily inbuilt in the relaying unit. And you have to give simply voltage and current. 3 voltages. That means, so to say, 3 voltages and neutral. And 3 currents. And if at all you want to give, you can give the neutral current also. I'm telling if at all because neutral current can be calculated by numerical relay also, because neutral current is IR plus IY plus IB divided by 3. So that is not difficult for any calculator. Numerical relay is a calculator. Numerical relay is a computer, so it can calculate. So these quantities are fed. So with this, the distance as principle is over. What is the principle of distance is over? So to say, it looks very good. It does not suffer from many disadvantages as suffered by overcurrent relays, right? Its setting procedure is very easy. All these things we have told. But yet, there are many problems in distance measurement. Many problems in this distance measurement. We'll take one by one. We mean that the impedance measured by the relay is from relaying point to the fault point. But we forget about fault resistance. You see, when double line fault occurs, double line resistance, impedance, plus the fault resistance, that is the flashover resistance. Well, that you may forget because that is just 2 to 4 ohms. But when line to ground fault occurs, it is 20 to 50 ohms. So that is added. That is added in the measured impedance. Whether your formula and your quantities, you have not considered that. You have considered only Z1, that is the line, but it does not measure the line impedance, it measures the fault impedance also. So what this fault impedance do? What what this fault impedance do that we have to that we have to see. So before we see the problem of fault impedance, we see the another problem is that of direction. All distance relays have to be directional. And as we have discussed, only more relay is directional. Therefore, in earlier days, more relay was used to be a universal relay. So if we do not use the directional relay, what happens? So for that we refer to figure 8.23. I've got a relay R, right? It sees towards D, it sees towards C, B to C. Fault is at F, but because the generator is on another side, generator 2, it will feed the fault. It will feed the fault means relay will measure the impedance. And as we had talked, relay will measure the impedance in third zone. And in third zone, it will fall within the impedance characteristic because impedance characteristic is a circle. It will fall in reactance characteristic also because any impedance that is below reactance characteristic straight line is measured by the relay. Ohm also is non-directional, right? So all relays will mal-operate for F. Why I am saying mal-operate? Relay R should not operate for fault F. This relay R, right? Uh, my cursor is not coming fast. Yes, this relay R does not operate at for relay. I mean, it operates for relay F. That is the difficulty. Because this is in third zone, but third zone is in characteristic. So relay R operates. It should not operate because if relay R operates, it will break its own breaker 3. And if it trips breaker 3, bus bar B will be isolated from power being fed by generator 2. Being fed by generator 2. Right. So it has to depend on power being fed by generator 1 only. Probably the power may be so high that generator 1 cannot feed power to bus B. So the power system may become unstable or you may have to do a load shedding on large scale. So direction is very important thing. Relay has to be directional and therefore we are using more relay and yet better relays are used that we will see one by one, right? Fault resistance, as I was telling, the relay measures fault also. And when it measures fault, what does it mean? It means this, that my impedance circle is this. OZ1 is the fault has occurred at A, and therefore that means at threshold point A, and impedance measured is Z1. But impedance measured is not Z1 because some fault resistance RF is there. In any case, except for triple line to ground fault because it is only three, earthing switch is made on, inadvertently made on when circuit breaker is on. Therefore, in that case, only RF equal to 0. Otherwise, for double line fault also it is there. So, relay measures OZ1 plus Z1 RF. See, RF is horizontal. R line is horizontal. So, relay measures ORF. OD, whatever you call, it measures OD. So the point goes out of the characteristic. Looking otherwise, for making the relay to be on the threshold, it cannot measure up to Z1, it can measure up to less than Z1, it can measure 10% less or 5% less. So that is the underreach of the relay. So, because of fault resistance, relay underreaches. This is the very first or the second important problem that it reaches, it underreaches. It does not protect full line length. It underreaches. It has to it has to reach up to 100 kilometer, and it is only up to 80 kilometer. That is the problem. So remnant 20 kilometer, who will save? Who will protect? That is the great problem for ZF. That is the fault impedance, right? Therefore, one has to take care of this ZF somehow. Or if you calculate ZF, you have to consider this ZF while setting the relay characteristics. If you see BC is equal to AD, BC is equal to AD, that means relay measures only up to AB, only up to OB. That means AB is the person, AB is the underreach. AB divided by OA into 100 is the percentage underreach. This is the percentage. So impedance relay with reference to direction, we have seen it is useless. With reference to problem of fault resistance, also impedance relay is useless. Right? Impedance relay is also useless. This I've talked. So what should you do then? What you should do? So we go to figure 8.25. What should we do? See, if you compare different types of characteristics, standard characteristic, reactance, impedance, mho, and ohm, then you will see that reactance characteristic is immune to fault resistance because it can incorporate any amount of infinite amount of fault resistance. You see, it can, because it is not calculating R, it is calculating X only. So where you want to calculate X only and you do not want to calculate R, or where R is very high, reactance is better. The application is short transmission line. If you have got 20 kilometer, say I was telling to Ukai hydro to Ukai thermal is 6 kilometer long line, 220 kV, 6 kilometer. So impedance of 6 kilometer line would be maybe 1 ohm or even fraction of ohm. And if the earth fault occurs, earth fault is 20 ohm only, because earth fault is flashover, tower, soil resistivity does not differ. So the fault resistance is highly comparable to the this line resistance, the line resistance up to fault. Therefore, in such cases where the lines are short, reactance is better. So often when short line is there, in fur zone, people go for reactance relay. And you are protecting fur zone, reactance relay is good. So the application of reactance relay is in first or at the most second zone. Third zone, you cannot reactance relay. If you go to more relay, it cannot incorporate fault resistance. If you go to ohm relay, you can see it can incorporate small fault resistance, A to something. B, AE is equal to, AE is equal to, I will tell AE equal to what? Sorry. AE is equal to what? AE equal to what? AE equal to AB, that is percentage, but AB is not equal to AE. AE is less than AB for the same percentage under reach. That means percentage under reach for more relay is less. That's why more relay with reference to direction is good. With reference to fault resistance, it incorporates small fault resistance. May not be for earth fault, but at least for phase faults. So More relay is good. No doubt, if you want to increase the uh, fault, fault resistivity, the resistance that it covers, resistance, the uh, resistance that incorporates, you have to decrease the angle from 60 degree, you have to decrease to 45 degree to 30 degree, etc. But if you do so, it is going to suffer from the problem of overload and power swing, which we are going to see further. So we have to make compromise everywhere, right? Therefore, compromise is the engineering. Compromising things is itself is engineering. So out of these four characteristics, Mo is the best. If we go further, best characteristic is quadrilateral characteristic. But quadrilateral is not standard characteristic, it is non-standard. Quadrilateral characteristic cannot be built, cannot be designed, cannot be rigged up by numerical or by static or electromagnetic relay. It has to be uh, prepared, it has to be manufactured by numerical relay only. So only when numerical relay came into market, this was possible. No doubt, uh, three quantity numerical relay. We are feeding K minus V and V, K minus V and Ki. Instead of that, if you feed three different quantities of combination of current and voltage, quadrilateral characteristic can be built. And my great guru, Dr. Date, I consider him the best teacher in the world probably. I have yet to see a teacher of his category. He liked the project very much and he made one ME student to do the project on quadrilateral characteristic with three inputs, static relay, not numerical, static relay, that he had done. But this is not quadrilateral. This is giving a notch. If you see at one point, there is a notch. I don't know why this cursor is not coming fast. I have to move it down here and there. Yes, now it has come. This notch is there. This notch is not possible in static relay. Therefore, this type of relay, quadrilateral relay as it is named as, there are many characteristics. Slowly, probably we may talk. There is lenticular characteristic. There is elliptical characteristic. There is quadramo characteristic. There are many characteristics which can be built and which have many advantages over our four standard characteristics that we have talked about. That is the impedance, reactance, mho and ohm. These new characteristics are standard. And because our system is expanding like anything, whole India is connected now. Kashmir can feed power to Ahmedabad. When such a thing is there, that is very good. You will like it. That if Gujarat has no power, Kashmir will feed. But the problem is when there is a problem in fault in Assam, complete nation will feed that fault, and therefore that fault current will be very high. Fault current is high to the tune of 30,000 MVA or so. And when such a large fault current is there, CT, transformer, forget about transmission line because there are no turns. But where there are oil, these, that, etc., material used, there are turns. A specific construction is there. That is CT, PT, circuit breaker, and isolator, and this transformer will be badly damaged, right, because of this. Therefore, this relay, which is good with reference to fault resistance, may not be good with reference to power swing. But this fellow, quadrilateral relay, has taken care that it is comparatively good with reference to fault resistance, all the way it is good with reference to power swing. What is power swing, that we are yet to see. We are talking yet about second problem, and today we are going to talk about only two problems. So what is this problem of power swing that you should understand, right? What is the problem of power swing? Power swing problem. I have told here itself. Power swing problem is this, that normal load is P. You see, normal load P, you try to understand why it is shown at P. It is shown at P because our normal power is 0.8 or 0.85. So angle between R and that Z line is about 36 degree or 30 degree. Therefore, P is shown at 30 or 36 degree to R line. And point P normal load is there. That means voltage is normal, current is normal. Now overload occurs. 50%, 30%, 60% overload occurs. Now when overload occurs, voltage remains more or less constant. So voltage is constant and current is more, therefore impedance is less. And it is quite possible that impedance will enter into at least third zone. And if impedance enters into third zone, the relay will operate in third zone and tripping will occur. It was not a fault, it was an overload. The relay should not trip, relay should not operate, relay should not trip the breaker because this was not a fault. So you have to take some actions. So one action you can take it, the third zone reach has to be properly designed. Third zone reach cannot be very large. But this quadrilateral characteristic people has done a very good thing. They have kept a notch like this, you see. This notch gives the advantage. This notch. What this advantage it gives? This P point will come nearer. Overload will be there. It will come to P dash and then it will come to P double dash. When it comes to P dash means this extended line. It starts giving an alarm. Relay will give an alarm, letting you know that overload is occurring. You have to take actions. If you fail to take actions and overload is developing very fast, it will come to P dash, P double dash, and it will cross P double dash, then the relay will trip. But you see, to cross, I mean, for the relay to cross P double dash is very rare because transmission line can be overloaded up to 200%. Because of overload, what is damaged? Because of overload, what is damaged is insulation. And for transmission line, the insulation is that suspension insulator and air. So air is becoming hot because of overload. So that hot air being less dense will go up and the cold air with good dielectric strength will come there. So that convection current will continue. So air will never be damaged. You have not to go to repair the air. Right. And the porcelain insulator has very high temperature withstand capability. So that way transmission line can take high overload. I don't mean to say that you should allow transmission line to take high overload. Power is flowing from station A to station B. Overload is occurring. Station B person will come to know that overload has occurred. So he will take necessary action to shed the load. and to bring the load back to normal. But till then, the relay should not operate. That is our concern. That is the concern of a protection engineer, my dear friends. So direction and volt resistance. With this, my talk ends. This has been spoken by Swami Chinmayanandji. This sentence is spoken by Swami Chinmayanandji. Don't put the key to your happiness in someone else's pocket. That is what the mistake we are doing. Every one of us is doing this mistake. I am not happy because the other person is not giving me more money. I am not happy because the other person is not giving me good food. I am not happy because my wife does not love me love me better. She does not love me. Therefore, I am not happy. So I am putting the key of my happiness in someone else's pocket only. So you will never be happy. आप पूरे जीवन में दुख में ही रहेंगे. You will be in unhappiness only. So Swami Chinmayanandji says that keep the key in your pocket. You should be happy by your own. You should be happy in your own way. Osho says that dance. Osho says that dance. Hear music. Be happy like that. That is what he says. With that sentence of the day, we end this. You might say that I'm telling the same sentence again and again. I'm saying because if the thing is heard and said many times, it is remembered. One thing. And second thing, that some people are seeing only one or two videos. They are not seeing all videos. So for them, I must tell that this lecture, this education on distance protection of transmission line, and it is not going to be only distance. After distance, we are going to talk of the generator protection, and after generator, we are going to talk of transformer protection. Then we are going to talk of the induction motor protection. Then we are going to talk of the bus zone protection. Then we are going to talk on CTPT. Then we are going to talk on circuit breakers, right? And the current breaking devices. So many things we are going to talk about in this subject. And if at all time permits, we may touch a topic of overvoltage protection also. That will all take 150 videos. This, as I told you, this must be my 30th video or so. I have to give some 150 videos, and then only I will be able to complete this. But the platform of providing these 150 videos to you all is given to me by edupme. Therefore, I should not forget edupme, and you should not forget edupme, because these this knowledge is given to you by edupme. So, friend, thank you for the day. I don't know whether I should say good night, because some people sleep early. I sleep at about 12:31 p.m. So it is not yet night for me, but some people sleep at 10:30. So good night for them. When you would be hearing this video, it may be morning also, I don't know. But at least for now, it is good night. Good night, everybody.